As a reminder, with all the educator resources that we've talked to you about up to this point, you can find those actually right on Dr. Bart's Intro to Python course in the yellow box located in the bottom right-hand corner of the screen, or through our community at community.vscodeedu.com, or by using the QR code that's available in the corner. Once you register as a verified educator, you'll have access to all the things you saw in a plethora of other resources and engage with other educators within the community. We know it's something you'll love, and so please feel free to join when you can. All right, Dr. Bart, I'm wondering if you can take us through an example and talk through really the foundations of your Python curriculum.
Great. I'm so excited to talk about this. So hopefully you've heard about Python before, but just if you haven't, it's probably one of the most popular programming languages in the world, depending on how you want to measure these things. Certainly right now, it's at the top of the TIOBE index for the past year or two. So Python is a very popular language for introductory courses, and it's a very popular choice for CS1. Now, one of the reasons that Python is so popular is because it has so many different uses out there. It's used in scientific computing, for data science, for machine learning, for analyzing data, for building web servers, websites. It's used in popular game development. It's also used for a lot of back-end scripting. Python has a lot of different applications, and there's a huge ecosystem of libraries and tools out there for professional Pythonistas to develop things, but it also has a lot of pedagogical applications, and it's very useful for a younger audience, we found. When we first started trying to teach Introduction to Python courses in the schools I've been at for the past decade, we found very few curricula that actually fit all of the use cases that we wanted to have. We were looking for a modern Python curriculum, one that would be teaching modern Python, the most up-to-date materials, and would have all the things that a teacher would need, not just the lecture slides, but also activities and the programming problems, the rubrics for grading projects, everything that you might need. And when we looked around, we couldn't find an open source project, anything that was free, that we could use as a base. And that was when we decided to try and make our own. And that's led to the Python Bakery curriculum, which is the textbook, the curriculum materials that we've put into VS Code EDU. So we'll talk more in detail about the exact details of the course, but first let's talk about a bit more about the curriculum in large. So one of the main things we wanted to do was try and create resources that would follow best computer science practices that we know about. And if we looked around and saw some of the existing materials that were out there, there were a few projects that were, open source free trying to teach Python. We kept finding that a lot of them seemed to have some number of bad computer science practices in them. And these are principles that we wanted to elevate from the very beginning of the course. Now, obviously, students aren't always necessarily ready on day one to understand the value of variable names, but we do think that there's value in signaling to the students that variable names matter, that code quality matters, things like unit testing can help, and we've incorporated that throughout the curriculum, even when there are places that students have to sort of understand that they're going to get more depth later. Just looking at an example from one of the resources we had found originally, this is just one page about for loops that students would be looking at. And there are single letter variable names, inconsistent capitalization of the variable names. In some cases, they don't even try and use underscores or capitalization. It's very unPythonic text. And there's also very little emphasis on things like functional decomposition, avoiding global variables, unit testing. These are things that we consider to be critical for teaching young computer scientists. So we've made a real big part of the curriculum to try and focus on these ideas from day one. We also wanted to make sure that we were teaching as much modern Python as we could, authentic things that modern developers actually use. And this has had some pedagogical benefits as well. So for instance, a new feature in Python for the past 5 years has been static type annotations. And this has been very exciting because it helps with the students' pedagogy quite a bit too. There's a lot of research out there about the benefits of static typing, not just for experts, but also for novices. So throughout the curriculum, whenever they're defining functions, the parameters have types and they have return types. We also have students defining data classes instead of regular classes. For those familiar with object-oriented programming in Python, it can be a little bit clumsy. So instead, we managed to massage over a lot of those hurdles with data classes. And it does require some extra syntax, both with the static type annotations and the data classes. But we found that this actually can help students act as kind of like a lightning rod for their thoughts. Be like, oh, this is how I define a class. It has this specific syntax and it requires me to do these things. all of which I think ends up being a benefit, especially with the flexibility and power that comes with using things like data classes. We emphasize collection-based iteration with for loops over while loops. So this is just more of how regular Python teachers, Python programmers use Python. We're trying to be in line with like those kind of industry practices where it makes sense. We also have been using as much of the research literature on computer science education as we can possibly fit into the course. Whenever we come across a new understanding, a new research result that has empirical data backing it up, we'll try and integrate it into the curriculum. One of the big examples of this is we used to try and teach variables using a box metaphor. And although we touch on that lightly, we focus a lot more on explaining variables as being tags. You can take a tag and reattach it to new values. This is, according to some research that we found by Fellini, this was actually able to avoid certain misconceptions that students have because the nature of boxes are very different from the nature of tags and how much data can fit into a box. We've also incorporated things like stack heap diagrams and worked examples and having nice schemas and templates for students. These are all things that we took from the literature and tried to integrate into our curriculum. And it's an open source project that we're always trying to iterate on and develop. So the goal is to keep trying to improve things as we improve our understanding of how people learn computer science. One of the other neat things we have in the curriculum, and this is a separate project at some level, is Pedal. So we often had students working in large class settings where we were only able to give minimal amounts of feedback from the humans. So we needed a tool that would be able to give them reliable feedback and check that their code was correct. And early in the semester, we can't rely on things like unit testing. So we developed this tool, Pedal, that would be able to inspect students' code and through the use of customized grading scripts, provide reliable feedback. And this is not some artificial intelligence project. This is just a lot of very complicated if statements doing a lot of important checks to make sure that the student's code meets certain requirements and then also be able to point out things that they might have done wrong. Now, Pedal is an independent project, and you can see the GitHub and additional resources there on our website. It's open source, it's free, it's just a thing that you can use independent, but it's also naturally integrated into VS Code EDU, which I'm really excited about. Just looking a little bit more closely at sort of an example of the kind of things that Pedal lets us do. When I was first teaching Python so many years ago, I had students come to me and complain and say, Dr. Bart, your unit tests have broken my code. And no, my unit tests didn't break your code. They're the messenger. Your code was broken, and my tests are explaining that. But from the student's perspective, when you look at the default output for unit tests in Python, there's a lot of cryptic text and confusing symbols, and it can be very unclear what actually went wrong. I mean, it shows the instructor codes as being instructor lines of code as being the problem rather than the students. So one of the things, just as an example, that Pedal is able to do is it shows, hey, I ran your code and I expected it to be this, but instead it was this. Or it can say something about like the error that it received, but it's able to transform those exceptions, those output messages, and give you a bit more context explanation. And we have this for a number of other issues in the code base. And again, this is an open source tool that we're always trying to improve and add more features to. Python is a really exciting language to teach with, and I think this curriculum can serve as a base for a lot of different kinds of projects. Over the years, we've done a lot of different things with this course. We've had students making websites, we've had students making games, we've had them do data science in Jupyter notebooks, we've had them accessing real world web data. I think that with this foundation of just the basics of functions, for loops, if statements, there's a lot of great connection points that students can use to extend and build on their knowledge. Now, I don't want to make it sound perfectly rosy. There are a lot of complicated aspects to trying to teach Python and CS1. I just wanted to go through a few that I thought might be relevant for new instructors trying to pick up this curriculum. Some of them are Python specific problems. So for instance, truthiness rules, depending on what languages you're coming from, can be very confusing. You might find it a little bit strange when you see the syntax that allows you to use a non-Boolean value as a conditional, and that's without requiring any additional conditional operators. So a list, for instance, if it's empty, counts as a falsy value. And the textbook goes into all of this. If you were reading ahead of the students, you'll see in chapter 3 a thorough explanation of how the truthiness rules work, what's happening, how they interact with if statements, some problems that can happen very easily because of them. Something that might be a little bit more surprising if you've done a lot of Python before is the static typing. Static types are a relatively modern feature of Python, and the type system is bolted in. So if you're coming from languages which have much more sophisticated type systems, you might find it very surprising sometimes how they work. There's a lot of little gotchas that some environments will straight up ignore, right? The type system is an optional feature, and it follows a lot of the same rules as the rest of the Python language in a way that a lot of type systems don't. So it's possible for students to make a lot of kind of mistakes. This is one of the reasons why our pedal system is so helpful, is that it's able to give feedback specifically about those static types. Another sort of Python specific issue is that we can have issues with the object-oriented programming aspect. Python has a somewhat clumsy object-oriented programming setup. Its constructors, for instance, are prefixed and suffixed with double underscores, and it's named init instead of the word constructor. There's a whole self variable that must be passed in as the first parameter for every method. It can be quite confusing. And this is why we steer clear of regular classes and use data classes, which manage to hide away most of this complexity. But when you want to start getting to more complicated parts of the OO system, you may have to start touching on some of this. Now, there are also general issues in teaching a CS1 that if you're not familiar with, can take you by surprise as someone who might have some prior experience themselves. One of the biggest I always see every semester is students confusing assignment statements and equality tests, because in math class they mean one thing, and in computer class they mean something completely different. But assignment statements are an updating, a setting of a variable, and equality tests are used to compare values in a conditional context. And syntactically, they're very different. In Python, you have an equal sign versus two equal signs. This can cause a lot of confusion, although not nearly as much confusion as I see students having around functions. We consider functions to be so important, we cover them starting from week 2. And the students are using them throughout the semester. We teach unit testing and a lot of other solid ideas about functional decomposition. But with this comes terminology like arguments versus parameters, understanding how to pass a value into a function and return a value. And students will perpetually mess up the terminology for things like saying call a variable instead of calling a function and accessing a variable. So you have to be really vigilant with your novices that they're developing the right language and that they have the right mental models. There's also always a lot of issues that students have with aliasing and data mutability. Understanding the difference between a value and a reference to a value can be very confusing. Python additionally has several complicated little nitpicks. The append method of lists will return the value none instead of the list. So the example here is us actually clobbering the reference to the array, and it seems perfectly reasonable, but it doesn't work that way. It's just the way that Python is coded. And again, these are the kind of things the textbook goes into. If you're reading along with the students, you will see these same things, but they can take you by surprise depending on your prior experience. I've been teaching for, about a decade now, and I have been teaching Python specifically for most of that time. Here's my advice for anyone trying to teach with this curriculum. Some of it's just very independent and general from this specific language and this particular set of materials, but I think they're at least my advice. First of all, never be afraid to slow down your learners. Think about first, can they even explain the problem they're trying to do? A lot of the time, maybe half the time, I have students who come to me, sort of lost in the woods, and they haven't really thought about the problem they're actually trying to solve. They haven't thought about what their code should look like. Slowing them down and asking them to just read the prompt, asking them to just read it out loud to them, make sure they don't skip parts, because my students will often filter very aggressively and skip over important details. Also asking them to step through what their solution is. Have them take out a piece of paper, write down pseudocode of what they want to do, thinking about how the data gets transformed rather than just trying to think of individual syntactic constructions. And one of my favorite strategies is make them write some tests. Students never want to write unit tests before they try and write the solution, but this is something that I think can force them to understand what is this problem actually trying to do. If they can't write tests, then they probably don't understand the problem well enough to solve it. Having them slow down and go back to do these steps, I think, is key. Another thing that I found to be very helpful for novices who are trying to just get a handle on the nature of coding, introducing schemas, patterns, templates. When we teach for loops, we have a bunch of loop patterns that they can use and then compose with. We also have patterns related to if statements and other syntactical constructs. And this is something that they can sort of build on, that they can then enhance their understanding of by composing and combining. Another major thing that we've really gotten a lot of value from, types are a big deal in programming, helps us shape our understanding of what the data can and cannot do. Forcing students to use strong static typing can help them avoid certain kinds of problems. They have to really know what kind of data are they working with. Another really great set of features in a modern course like this are debuggers and visualization tools. VS Code EDU has some great tools built in, and I think that's a really powerful thing. A lot of novices are confused by how debuggers work, but spending a bit of time using one can actually give them an entire set of, tools that can solve very difficult problems. I think spending some time walking them through how you debug things, how to use these tools, that really pays off. But there is no greater piece of advice that I have than practice, practice, practice. If you would like to learn a foreign language, you have to go live in that country and speak that language. And it's the same thing for learning how to program. You have to actually write code. And eventually we can use that to develop a conversation about computer science and software engineering. But it all starts with understanding those basics of just how a program works, reading programs, writing code, running the code, getting that feedback. There's no replacement. There's no lecture. There's no textbook. There's no quiz questions that we can use that fulfill the same role as having them just write code.